This is an AP Chemistry presentation on the gas laws. I have used material developed by J. David Robertson and have considerably changed it. Let's talk about pressure. Pressure is the force applied to a particular area. In other words, force divided by area. The conversion units that we use with respect to normal atmospheric pressure, we call a Pascal a Newton per square meter. 1 atmosphere then, which is normal atmospheric pressure at sea level, is 760 millimeters of mercury, also called 760 torr. This was originally measured by Torricelli using a mercury barometer, and he found that in a closed evacuated tube, mercury would rise to a level of 76 centimeters or 760 millimeters at sea level. So that is set. Atmospheric pressure, 1 atmosphere, is 760 millimeters of mercury. 1 atmosphere, more modern way of measuring it, is 101,325 pascals using the SI units. And of course, we use the kilopascal typically when we are measuring with digital pressure gauges. So 1 atmosphere is 101.3 kilopascals. Manometers were typically used to measure gas pressure, and either mercury or xylene was used to measure relative pressure. In a closed manometer, that is, with no way for atmospheric pressure to influence, you have a vacuum above the liquid that is moving, and you can measure changes in pressure by the changes in height. This is absolute pressure. If you leave the manometer open to the air here at the top of the tube, you're going to get relative pressure, that is, pressure relative to whatever the atmospheric pressure is. So you also need some sort of Torricelli or digital barometer to measure atmospheric pressure if you are going to use this kind of manometer. This is Boyle's original design for studying the relationship between pressure and volume of a gas. It was essentially an open manometer. He had this tube here, and he poured mercury into the tube, enclosing a gas in the sealed end. He then kept adding more and more mercury to increase the pressure on the gas, and as you can see, the pressure went up as he added mercury, and the volume went down. As the height of mercury and the pressure increased, the volume then decreases. Boyle's law, if we chart it out, total pressure here against volume of the gas here, we see that we have a curved line which looks very much like a reciprocal curve. The pressure is proportional to the reciprocal of the volume. Therefore, the pressure times volume is a constant. Any point here, as you can see, the volume here is 4 and the pressure 0.3. If you reduce the volume to 2 liters, you find that the pressure doubles. We can also say at any point on this line, the pressure times the volume is a constant, so any P1V1 product is equal to the P2V2 product. Boyle kept the amount of gas and the temperature constant. You can ask yourself, was this a good thing to control? Is it necessary to control these two variables? Now, if you graph the pressure against the reciprocal of volume, you will get a straight line. So, you can practice. A sample of chlorine gas occupying 946 milliliters has a pressure of 72.6 kPa. What's the pressure in kPa if you reduce the volume to 154 milliliters? Now, if you think about it, you realize you're going to have to increase the pressure. We use P1V1 equals P2V2. It's always a good idea to write down all of your variables and your unknown before you begin the problem. So the pressure originally, the volume originally, you don't know the final pressure. You do know the final volume, 154 milliliters. You solve for P2, and that is P1V1, this product. You divide both sides by V2, and you get P1V1 over V2. That's where you now put in the variables, the numerical value of the variables, 72.6 kPa, 946 milliliters, and 154 milliliters. Milliliters over milliliters is 1, and we come up with 446 kPa. As we expected, the pressure is going up. Now, gases can expand and contract as the temperature changes. What does using a good seal control here? What does the constant mass of the seal control? If you think about it, the good seal keeps the amount of gas the same, whether at low or high temperature. And if the mass doesn't change, then the pressure isn't going to change. So we have kept the number of moles and the pressure constant in this. We find as the temperature increases, the volume increases, and it does so linearly. We can, at different pressures, we can change the temperature, measure it in Celsius, and see that the volume goes up linearly at all 4 different pressures here. Volume is proportional to temperature. That must mean the volume is equal to a constant times the temperature, but we have to measure from this point, which we call absolute zero. Absolute zero is 273.15 degrees Celsius lower than the freezing point of water, 0 degrees Celsius. And so our working equation is V1 over T1 equals V2 over T2. So here's a practice problem. At what temperature will this gas, 2.80 liters at 125 degrees C, what temperature will it occupy a volume of 1.54 liters? Now, if you think about it, you realize that since the volume is going down, what has to happen to the temperature? It must go down. We use the working formula from the previous slide, V1 over T1 equals V2 over T2. We write down our known numbers. We remember to always put this in Kelvin, so we add 273.15 to the Celsius temperature. We write down our volume, and we solve for the temperature. T2 must be equal to V2 over V1 times T1. What we've done here is we have multiplied both sides by T2, to put that over here, then we multiply both sides by T1, and divide both sides by V1. And that gives us our working equation for the T2. We plug in the numbers in units. Liters over liters is 1, and our answer is 219 Kelvin. If the problem asks us the answer in Celsius degrees, we have to then subtract 273 to get the Celsius temperature of minus 54, and notice the temperature has gone from 125 to minus 54, a decrease as expected. We now go to Avogadro's law. What must be held constant if we're going to study the volume as a function of the number of moles of gas? The volume is proportional to the number of moles, so the volume is constant times the number of moles. And therefore we must be letting the number of moles change, letting the volume change, so we're going to have to keep the pressure constant and the temperature constant. Avogadro, remember, found that equal volumes contain equal numbers of molecules at constant temperature and pressure. Our working equation is V1 over N1 equals V2 over N2. So our question, at constant temperature and pressure, if 3.2 grams of oxygen is added to 4 grams of oxygen gas in a balloon, to what volume will the original 1 liter expand? We now solve for V2, which is going to be V1 over N1 times N2. We plug in our numbers and units. Grams over grams is 1, and the answer is 1.80 liters. And that makes sense because we added more oxygen. In fact, we almost doubled the amount of oxygen gas, and so we will almost double the volume from 1 to 1.8. We can also use Avogadro's law as the basis of what we call constant temperature and pressure gas stoichiometry, which is probably the easiest kind of stoichiometry problem to solve. For instance, we know that equal volumes contain equal numbers of molecules at constant T and P, so the equation 3 moles of, or molecules of hydrogen reacts with 1 molecule of nitrogen to form 2 molecules of ammonia could also be said 3 moles react with 1 mole to form 2 moles of ammonia. Now that happens at any temperature and pressure of these molecules. But if we have constant temperature and pressure, we now know that the mole ratio and the volume ratio must be the same. So 3 volumes of hydrogen will react with 1 volume of nitrogen to form 2 volumes of ammonia gas. Here's a practice problem. Ammonia burns in oxygen to form NO and water vapor. How many volumes of NO are obtained from 1 volume of ammonia at the same temperature and pressure? We first, of course, need a balanced chemical equation, which you see here. 4 moles of ammonia form 4 moles of nitric oxide. Oh, well, that must mean that the ratio of moles is 1 to 1. And at the same temperature and pressure, that must also mean that the ratio of volumes is 1 to 1. So 1 mole of ammonia gives you 1 mole of NO. At constant temperature and pressure, though, 1 volume of ammonia will react to form 1 volume of NO. This leads to the ideal gas equation, and we will start that on the next show.